is from Infinity Ward. And before that, he worked with Arnhem over at Electronic Arts on Medal of Honor. And obviously working on the Call of Duty something. Which you probably can't tell us.
I can't tell you anything about, or even if it is Call of Duty. Yes.
Whoa.
If it comes out, it's not called Call of Duty, we will all be surprised. All right. But it always has a subtitle of some sort. Okay. He is going to give us a talk today in physics simulation network games. So Duncan, go ahead.
So, like I said, I'm Duncan Adamson. I'm the senior physics engineer in Infinity Ward, working on an unannounced title that you can all guess at. And yeah, I'm just going to talk about physics. It's basically what I do, and then particularly how it relates to network games. Before I start, I've done a number of physics presentations over the years. I always like to start with the following slide. There's a lot of highly amusing words in physics simulation. If you're going to giggle, giggle now. Otherwise, when I say penetrating rigid body later on, I expect deathly silence.
Okay.
Otherwise, so first I'm going to start with what this talk's not about. I'm not going to talk about a kind of low-level collision detection. I'm not going to talk about capsule versus triangle mesh collision or anything like that. If you're particularly interested in that, I can only recommend this book, which is absolutely awesome, by Krista Eriksson. If you like kind of those low-level physics details, Minkowski subtraction and Jacobian streams, all that kind of thing, get Krista's book. It's fantastic. What I am going to talk about is basically how to build a physics simulation from the ground up, as we would in a normal AAA title for console, and then the relevant parts of it that show up when we start trying to do network simulation. So first of all, I'm going to start. Why did that not sync across? Did I?
It might take a while.
Oh, that's weird.
Is it you?
No?
There.
Oh, there we go. Okay, fine. So,
Oh, it's disconnecting you. All right, we might have to disconnect the cable.
there we go. Play from there. Okay. So, first of all, we'll kind of start with the ubiquitous kind of AAA object. Hey, we want to put a crate in our level and we want to move it around, or maybe we just want the player to collide with it, or maybe we want to destroy it. But whatever it is, we pretty much are just talking about rigid body physics simulation. So we're not doing cloth simulation, we're not talking about fluid dynamics or any kind of seascape or anything like that. We're just talking about rigid bodies. So the fundamental rule of a rigid body is during its lifetime, it does not ever, under any circumstances, change shape. If you want to change the shape, you're basically destroying that rigid body and creating another one with a different shape. It is rigid. And then there's some other information that we can kind of tack onto it, where it is in space and how fast it's moving and how fast it's rotating around its center of mass. It's kind of your fundamental, is a rigid body. It's the primitive that we would use to kind of create something. The most important part of a rigid body, in my opinion, is the collision geometry. A lot of game teams try and use their render geometry, one of their LODs maybe, for their collision geometry. And it provides kind of a number of problems when you do that. First of all, the triangle mesh, it's very difficult to kind of calculate on the fly whether it's an open or closed mesh. So you don't really know whether there's an inside or an outside to your collision mesh. Instead, in a physics simulation, we really want to use some kind of mathematical primitive, a sphere, a cylinder, a box, any kind of convex hull, where it's very easy to tell whether something's inside or outside of that hull. It also kind of gives us the benefit then that we know that we have dimension to our shape. Whereas if you have a mesh, it's very easy to have a single plane sticking out, and those planes, when viewed end-on, are kind of infinitely thin. And collision against an infinitely thin object is kind of an undefined thing in most physics simulations. So if you're ever involved in this kind of thing, try and make sure that whatever system you're doing is kind of generating at least a version of collision geometry, preferably mathematically primitive based. Though when you're trying to do a terrain chunk, you usually are kind of restricted back to doing some kind of mesh. But at least then you can say the mesh is probably not moving, it's probably fairly stable. So now we can kind of create a rigid body and give it some decent collision geometry. And the next thing that we want to spec is, there's basically three types of motion that we can give a rigid body in a physics simulation. The first, there we go, is called fixed or static. It's the doesn't move, you shall not pass rigid body. Like they under no circumstances will ever be moved in the level. So standard for this is, hey, I've got a piece of terrain, some rolling hills, or a building in a cityscape or something. You know it's never going to move. So if we flag it that way, we can get some small CPU savings and some memory savings by doing that. That's kind of well worth doing. Kind of the next level up is, hey, I've got it's called a keyframed motion object, rigid body. And those are rigid bodies that the movement of the body is entirely controlled by some other piece of game code. If it hits something, it's not going to bounce off of it. It's not going to be affected by gravity. It's entirely game controlled. If you have two keyframed objects and you throw them at each other in a rigid body simulation, they're going to go straight through each other because their positions are entirely controlled by game code. And then finally, we've got the one that everybody likes, which is, there we go, dynamic rigid bodies. Dynamic rigid body is the one that everybody likes. This is entirely controlled by the physics simulation. So its gravity will make it fall towards the floor. If it hits something, it'll bounce, it'll spin. You can push it around. You can apply forces, all those kind of things. So those are kind of the three main categories that we can then give our crate or whatever other rigid body we're talking about. In addition, there's a number of other standard properties that we'll give a rigid body. First and foremost, it needs a mass. If it's a dynamic body, when it collides against something, particularly if two dynamic bodies collide against each other, if you have a truck and a keyboard kind of colliding against each other, you want the keyboard to go flying off and not the truck. So we want to get mass kind of pretty accurate. The problem that we tend to see with setting mass to real-world values exactly is we're still using floating point hardware, and if you've got, say, a cruise ship that weighs 100,000 tons or whatever, and then you're throwing a paperclip at it that weighs a couple of grams, you tend to get problems with rounding errors pretty dramatically quickly. So I always try to crush the masses in a little bit, like don't make any kind of ratios that are more than 1 to 1,000, 1 to 2,000, that kind of thing. It means that in games, if you're looking at a pencil on a desk that's dynamic, it probably weighs about 1 kilo. If you're looking at a big truck, it probably doesn't weigh more than a couple of thousand kilos, regardless of how big it is. And then it's just basically trying to get things predominantly correct in that. For keyframed and static objects, one of the ways that most physics engines kind of tag things as, hey, this is a keyframed or static object, is by setting the mass to 0. Some places use like OFFFFF or something like that, but 0 is a kind of a nice, easy thing to handle. You just got to be careful if you're ever trying to calculate the inverse mass, because one of the zeros bad things. Beyond that, we apply an inertia tensor, which is probably, if any of you get into physics, one of the hardest things to explain to a design team. It's effectively, you're telling the object how difficult it is to rotate around each of its 3 axes. So if you imagine being in Home Depot or Lowe's and picking up like a 12-foot long 2x4, it's really easy to rotate around the longitudinal axis, but really difficult to kind of lift up in the air. That's what an inertia tensor is fundamentally telling you. So if you set these up correctly, and there's usually a huge set of math code in whatever your modeling exporter is to calculate it correctly, then things kind of feel more realistic. They don't feel, it's one way to kind of get away from that uncanny valley kind of feeling of this isn't what I know a 2x4 or a piece of debris looks like from watching Hollywood movies. The other thing you can do is you can kind of break the real world thing. If people are expecting something to tumble end over end, you can make it do that by modifying the tensor. We also want to set the friction parameter on our rigid bodies so it slows down when it's on slope or otherwise kind of rolling against something. Friction, like valid values are 0, which is kind of a completely glass smooth surface. It's not going to slow down at all the way up to float max. But realistically, if you look at real world surfaces, they're pretty much limited to kind of like 1.2 as a friction mu, kind of dynamic or static. But as a good setup, you can pretty much just take any, like if you go to any real physics site on the web, you can find decent friction values, plug them in as your mu values if you've got a decent algorithm. It's pretty much what you expect, and then you just iterate a little bit on it. The next thing that we spec is normally called restitution, or if you're talking to a design team, bounciness. It's how much of the energy is maintained during a collision in the linear direction. So restitution of 0, it's going to have none of the energy is retained. Restitution all the way up to 1 just is more and more and more bouncy. Anything above 1, you've created the physics version of flubber. Every time it collides against something, it's just going to get faster and faster and faster. Don't do that, it's bad. In fact, I would recommend anything above about 0.9, you should probably be throwing warnings up on your designer screen, like, hey, what the hell are you doing? Come talk to me. The most common thing beyond kind of restitution above 1 that you ever see is somebody who sets restitution to 0 and then is surprised when it looks like their object is still bouncing. Almost always what's happening is this, where the object is coming down, it collides at a corner, and the restitution in most simulations only affects the linear velocity of the object. So linearly, we will have not applied any of the reflection back into the linear velocity. But angular, that's definitely going to still be there. So that crate that's just kind of hit the ground is now going to start rotating around its center point. And for a couple of frames, you're going to see, like again, there's nothing in contact with the ground anymore. So you're not going to get the feeling that most designers want when they set restitution to 0, which is the crate coming down, hitting the ground, stopping, and then kind of tumbling and falling. If you want that kind of behavior, you're probably looking at modifying the inertia tensor to make it harder for the object to rotate. But it's kind of one of the most common complaints. And finally, we can set linear and angular damping and gravity on gravity. Pop up in a moment. Ooh, that good, huh? I don't touch nothing.
It popped out of the screen again.
But anyway, so linear and angular damping and gravity, they're not really collision properties, but it's the kind of thing that you want to make things look realistic. Objects that travel through the air, they tend to slow down, so you want some kind of linear damping. If you've got something spinning constantly and you have no angular damping, it will spin on forever, and people tend to expect things to slow down. And then beyond that, there's normally you need to get gravity right. The biggest problem that we have with gravity is people are expecting what they see in Hollywood movies that they grew up watching. And almost always, all of those old movies were very slowed down, tiny scale models. So gravity doesn't react how people think it does. You often want to set gravity to something that is, you kind of need to tune it. So you kind of throw some rigid bodies in the world and then you tune your gravity. Maybe you need gravity lighter so that things kind of seem like they're being thrown out more. In very rare cases, particularly with vehicle simulation, you almost want the gravity to be increased. So let's just go to this one. So that's the kind of properties that we give a rigid body. So now we can simulate it in the world. The next thing that any design team will ask for is kind of the concept of a constraint. Most rigid bodies, when you're simulating them in the world, they've got 6 fundamental degrees of freedom. You can move them in the X, Y, and Z, and you can rotate them in the X, Y, and Z. By limiting these degrees of freedom or removing them entirely, we can get some really, really useful behaviors. The most common one is let's create a hinge, which is just a complete elimination of the X, Y, and Z movement and an elimination of 2 axes of rotation, and then a limitation probably on the 3rd axis of rotation. And then your door or whatever can now rotate around that hinge. Another common one that comes up is a ball and socket joint, where you're limiting the 3 axes of translation, but not the rotation axes, and then kind of swing around. If you then limit those axes of rotation, you can get what we normally do when we're creating a ragdoll, where basically the position is pinned, like the shoulder to the torso, or upper leg to a pelvis, but you want some kind of limitation on the angles that those bodies can move relative to each other, so that we don't get legs kind of bending backwards unnaturally. You can do more esoteric things like a rack and pinion, where the rotation of one body is entirely restricted by the movement of another body. Or one that seems to be coming up more and more these days is kind of pulley-based constraints, where you've got one rigid body's position is is kind of constrained by another rigid body's position, with probably some multiplier in there, so you can have like real world kind of pulleys. So we can now we kind of give our design teams access to create any rigid body and give them any kind of constraints you like. And that kind of makes us think, hey, we're done now. That's awesome. We can just throw a whole bunch of these in the world and everything's great. So normally what you do is you throw in 3 or 4 bodies into a test level, everything looks fantastic, and then you give it on and you say, okay, I'm done with my physics sim, it's great. First thing the designers do is they add 3,000 objects to the scene and the CPU will fall over. The reason for that is fundamentally that there's no, by default, there's no space partitioning in your world. So if you're talking about every rigid body needs to know about every other rigid body. It's an n-squared kind of behavior. If you've only got 3 or 4 objects, that's pretty manageable. If you've got a couple of thousand, it gets really big really, really quickly. So inside your world, the most important thing you can do is figure out some way of partitioning it. The most common is kind of a 3-step process. First of all, we kind of define a broad phase, which is a way of saying to the world, hey, I'm interested in something that's happening in this area. Can you give me the list of rigid bodies in the world that are overlapping this area or are close enough to this area that they might count? Normally this would be some kind of octree or quadtree. More and more common these days we're seeing axis line bounding box trees, AABB trees, but it's basically whatever kind of partitioning, whatever kind of data you want, so long as there's an algorithm where you can go, hey, tell me the things that are roughly in this box or in this sphere or something like that. So now we've kind of narrowed down from the 3,000 objects in the world down to only a few. That's awesome. The problem is the world itself, which tends to be only a couple of rigid bodies, sometimes even only one rigid body, that's like triangle mesh based because it's the terrain and it's buildings, and it tends to be 250,000, 500,000 triangles. Like it doesn't matter that you've only analyzed it, it tends to come up in, like it covers most of the environment. So you're going to be picking it up in almost any query, and it's crazy expensive. So we had the concept of a mid-phase algorithm, which, given a complex mesh or a complex bunch of primitives, then effectively does the same thing the broad phase does, maybe even with the same algorithm. But it's a way then of kind of limiting that 250,000, 500,000 tries down to only the ones that are relevant for the area that you're actively looking in. And then last but not least, we have what's called the narrow phase. That's where all the expensive math is done. So if this is where your triangle versus capsule code would be, or something like that. So now we can partition a world. That doesn't give us everything we want. Normally there's some concept of wanting to kind of prevent collisions between certain objects. Maybe you've got a world that's got some objects that want to block the player, some trigger boxes that pick up the player but other things don't collide against, some foliage that the player can walk through but maybe an AI sidecast is going to collide against. So we can kind of label bodies in one of a number of ways. The most common is just kind of give them a category of saying, hey, this is the player, this is a solid object, this is foliage. And then we can write a really simple, as optimal as possible piece of logic that kind of excludes non-interacting pairs. So then when we're ripping through the broad phase or through the mid phase or even through the narrow phase, you can kind of go, look, I don't even need to do the math. I know these objects will never collide regardless. Like I don't care. Like AI sidecasts never collide against trigger boxes. The player never collides against foliage. We're just going to let those completely, like it's just return false. Nice and easy. And that gives kind of a lot of nice tools. It's also really common to use this kind of thing for when you've got tightly constrained rigid bodies. If you have a ragdoll, like like say the lower arm and the upper arm, the rigid bodies are like to come pretty close to each other, may even be overlapping. You probably don't want them colliding, otherwise they're going to grind against each other. So you can just disable collision against kind of adjacent pairs. And then you're still going to get forearm against chest collision, but you're not going to get forearm against upper arm. Simplify your CPU and you get the behaviors you want. Filtering is kind of normally where we do this kind of thing. So now we've set up our world, we've got rigid bodies in it, and we want to kind of press play, kind of step the simulation forwards. There's a number of concerns that will come up with a physics simulation. First and foremost at the minute is the religious war that's kind of kicking off about whether we should simulate on CPU or on GPU with Compute Shader. And really my opinion is that it depends, like, use the right tool for the right job, as it kind of is with most kind of tech questions. The first thing you're going to want to check in any game engine is what are your available resources. It may be if you go and talk to the rendering team that we're GPU bound, in which case there's no point in moving your physics simulation onto the GPU, you're just making things worse, and then the CPU will be far more reasonable. That doesn't tend to happen at the minute, to tell the truth. Most of our compute shade is underutilized in most games, but definitely check first. The next thing will be what's the complexity of the scene? What kind of physics simulation are you actually trying to set up? If you have lots and lots of lightweight debris particles that are all similar to each other, then the computer shader seems like a fantastic idea. It tends to want to do 32, 64 things that are the same all at the same time. So if you can go, hey, these objects, like I've got 1,000 objects that are all the same, just batch them out. Compute shader is great. If you're making a racing game where you've got 20 cars and each one is interacting heavily with lots of other things and doing its own bespoke stuff, chances of you getting anything useful in kind of parallelism out of the compute shader are minimal. Then obviously we've got wanting to interact with game systems. It's fairly common when you've got complex objects in a scene that they want to, halfway through the step, make a call back into game code and go and find some information. Sometimes you can kind of cache that information off the beginning and pass it into the step, but often you don't know what it's going to call and you can't cache the entire game data and send it over.
So when you're doing the physics on the GPU, suppose you have a collision and the object's parameters change. You have to tell the CPU that, okay, this has
Yeah,
changed.
you would have to, well,
But
you don't
it's-
always, but yes, it's
But it's an expensive process to
Yeah.
send data back to CPU from the
Yes.
GPU.
So normally you wouldn't want to do that. Instead, you'd probably want to either keep that on the CPU, or in a lot of more modern cases, a lot of the events that are happening are things like you just want to play a sound effect or a particle effect when things collide. They're not really callbacks that need to happen halfway through the step. You can cache those together and just batch them back at the end in some step that you can process afterwards. So it's kind of important to delineate your events into things that need to happen now and things that are just, hey, here's the thing that happened during the step, handle it whenever. If you need to process stuff immediately, probably don't want to be doing that on the GPU because you're going to have to, like you say, kind of stop everything, send a message back to the CPU, collect your data, and that's a terrible, terrible thing to do.
But even if you're playing an audio, you have to tell, the audio will play on the CPU, right? It's not going to play.
Yes, I mean, you will definitely have to send some information back,
Yeah.
but you won't have to block on it. Like, you're not waiting for information back from the CPU.
Okay.
You could just send the information then, or you could cache it and send a block later on. Audio guys don't tend to want hundreds of events every frame anyway, so you could just
Yeah.
keep a small cache and then just send a couple back at the end of the frame. Last but not least, it's important to kind of know whether your simulation is multi-threaded on the CPU or not. Oftentimes you can get, like, if you are GPU bound, sticking something on single-threaded on the CPU may just make you CPU bound. So you're going to want to check and see, like, can we multi-thread this on the CPU? How many threads is sensible? There's always the law of diminishing returns. You get, if I use 4 cores, it's 3 times faster. If I use 6 cores, it's only 4 times faster. Like, how many cores is worthwhile setting? You probably don't want to give it, like, if you've got a big beefy PC, you probably don't want to give 16 CPU cores to the physics system. You're just wasting CPU in task overhead. It's kind of important to kind of figure out, like are we CPU, are we GPU, and are we single or multi-threaded? Next kind of question that comes up with every physics simulation is it deterministic? If you're just doing a simple particle effect or some destruction that you don't really, like, there's no impact on the game system, you don't need your engine to be deterministic at all. You can just throw stuff out, and if the ragdoll goes left on your machine and right on my machine, I don't care. But if you were writing let's say a racing game where we're recording exactly what input the player did, and then I want to play it back on someone else's machine, send it over to your PlayStation to see, then if we're going to re-simulate with exactly the same physics engine, you're going to want it to do exactly the same thing. And it's terrible if I happen to cut the corner absolutely perfectly, hit the apex, and I send you my thing and you look at it and I crash into a tree. I'm not going to be happy. So there are some engines out there that are deterministic, and there are some that are out there that are not. It's usually kind of decision that you're going to want to make right before you pick your simulation. NVIDIA's PhysX, for example, is not deterministic, but many of the ones out there are, and it really depends on what you want out of your simulation. The next thing that comes up, one of things, is continuous versus discrete simulation in a physics engine, which is, again, kind of difficult to explain, but I'll show you a couple of videos if these will play. I don't know if they will play at all. Let's see.
Put them on bottom.
Any luck? Oh, did it go?
No.
No? No, that's the next slide. That's the next slide. They're the two very similar. If not, I will just talk about it. But okay, fine. I'll just talk about it. So imagine these are awesome videos. So this is a simulation test I made a while ago. It's 3600 random physics shapes, kind of spheres and capsules and boxes of different sizes, and then we just drop them on a fairly thin ground plane. This is the continuous simulation version, where those 3600 objects, they all land on the floor and they bounce perfectly, and they all end up in a lovely, fairly stable pile. And this slide, which looks almost the same, is a discrete simulation where everything looks the same to start with, as everything kind of goes towards the ground. And then you'll notice that hundreds and hundreds of objects start to pour through the ground. So a discrete simulation, at pretty much every frame, the object is here one frame, and then the next frame it's as though it had been destroyed and recreated over here. So anything that was happening in the middle, we may have completely not detected. Or we may have 80% penetrated, in which case whatever penetration solver we have is just going to be pushing it further out that side. So in a discrete simulation, you probably, if you've got fast moving objects and you care about this kind of thing, you're going to have to write a lot of anti-tunneling code, which is usually just something like, hey, we moved it here, we care about this object, let's see, like, did we hit anything on the way? Either that, or kind of restrict objects' movement to less than half of their kind of minimum axis of size every frame, which means everything's moving pretty slowly. So you probably want a continuous simulation. They tend to be more CPU intensive, so if you don't care, you can get away in some cases with a discrete simulation. But most of the middlewares and high-end physics packages these days are using really, really good continuous simulation. They've been working on it for a number of years, and it tends to be almost as fast as a discrete simulation these days anyway. So I would advise a continuous one. Let's see, can I get to my next slide? Oh, there we go. So this is kind of what I was talking about, but kind of writ large. If you have a rigid body and you want to move it somewhere, if you have a continuous simulation, you want to move it there, you don't want to teleport it there. If you teleport it there, it might be on top of something, and then you've created a penetration. You might have moved it through some object and that you want it to collide against. So it's far more sensible instead, just before you do your frames update, to instead give the object enough linear and angular velocity that it's going to get to the position and orientation that you were expecting it to get to. There are cases where we do want to teleport, if you want to send something to the other side of the map, or if you really don't care about like what was in the way, but you've got to be really careful about not teleporting it on top of some things. And then kind of the kind of final thing that's really important in simulation is what kind of algorithm do you have to send objects to sleep. Normally, inside a simulation, you're going to kind of try and cluster your rigid bodies into islands of simulation that are kind of rigid bodies that may impact each other. So you've got a pile of debris in one corner and a pile of debris in another corner. That'd be two separate islands. If nothing's moved in those islands for a little while, we can send it to sleep. The CPU cost is literally nil. Like, we just go, it's still asleep, I don't need to do anything with that. And we only need to wake it up when another rigid body comes close enough and is moving that it might be colliding with it. If you don't do deactivation, then every frame you're literally having to process the collision detection for every single rigid body in your scene. So now we've got a simulation that we can step forwards. Everything looks really pretty. Like the user's really happy that they can see all this awesome stuff. But the rest of the game team's a little bit disappointed because all of their CPU is being used on making all this pretty stuff and they haven't got anything out of it. It's particularly relevant for other gameplay team members and people writing AI systems. They want to know information from the scene. So we also kind of give a variety of queries, which I would say these days are probably most heavily player and AI movement and sightline checking. But there are a number of other cases. The most common thing is I just want to trace between 2 points in my world. Tell me the things along this ray that I hit. The most default one of those is it's literally just we're casting a point along that ray. Like, is there anything on this line segment in the world? Is there anything in the way from the start to the end? The next kind of level up from that is, well, how about I stick a shape on there? How about I put a capsule or a cube or a sphere or a tank shape or something along that ray and kind of cast it through the scene and see, like, maybe you could say, hey, can my helicopter fit through this gap? Would be a common one. In which case you get a rough shape of the helicopter, you can cast it along that line. If it hits something, no you can't. If it doesn't, great, you can kind of move it through that gap. Most important thing here is there's no changed orientation along the ray in any physics API that I know of. You can orient the shape at the start point, but it's going to stay that orientation along that entire ray. So it's not good for saying, hey, I'm swinging this object or throwing this object through the scene and it's tumbling end over end and I want to know if it's going to hit something. That's not something that we can easily detect. But if you've got a bounding sphere for the shape, you can cast that bounding sphere through just fine. Kind of next major query that comes up a lot is, like, tell me, is this point or this shape penetrating something? Like, what's it penetrating? What would the direction be that I need to move away from in order to kind of get out of this shape? And how far would I have to move? You can also say, what's the nearest thing to this point or the nearest thing to this shape? That's kind of often useful if we want to kind of, let's say, teleport an AI to a location and you want to go, hey, I want to check that we're not teleporting them inside a wall. You could do a shape query for the endpoint, and if it doesn't hit anything, then great. And last but not least, it's not super important. It doesn't come up super often, but it's really, really cheap to query the broad phase. That's kind of its point. Is if you've got an axis-aligned bounding box-based broad phase, and you just want to say, hey, is there anything in this box? If you just do that at the broad phase level, if you can get away with that, that's fantastic, and it's super fast and super cheap, and you haven't gone down to the mid phase or the narrow phase at all. It doesn't come up very often, but when it does, you can save a lot of CPU there. When you are firing an array through the world, or any kind of query through the world, there's three kind of fundamental result collection algorithms that we use. The first is, hey, did I hit anything? And the only kind of result that you get back from that is a true or false result. You're not going to get any details about what you hit because you didn't really specify that you were interested in an object. It's like, do I have, like for raycasters, do I have line of sight, yes or no? We have the kind of closest or worst technique, which is if you're casting a ray through the scene, it's get me the closest thing I hit. I don't care about like the next thing that it would have hit, but I care about the one that's closest to me. It's really good if you're writing like if you want the reticle for a gun to kind of go red when you're pointing at an enemy. You kind of go, hey, what's the closest thing that I'm along the camera's line of sight? If it's an enemy, set it red. If it's not, don't. And then there's the most CPU intensive, which is, hey, collect me everything along this query. Like I want to know all the results. So obviously it's kind of getting more and more CPU intensive as you go down the list. The any can just bail as soon as it's found anything, it just bails from the algorithm with a true or false. The closest or worst, as soon as it hits something, it knows it doesn't have to check anything that's guaranteed to be further away than it currently got. So it can kind of effectively almost binary chop its way through the environment. Whereas the all, that needs to kind of test absolutely everything, so is very CPU intensive. And the kind of common questions that we kind of answer with queries are, hey, can my AI shoot this target? There we're just going to fire probably a ray through the scene with an any, and if we get something back, then we probably can't shoot that target. If we don't get anything back, then the AI's got line of sight, then it's free to shoot. Really quite cheap, and we do a whole load of these in our frame, probably every frame at the minute. When the player fires a bullet, or when an AI fires a bullet, we want to know what did it hit. Again, you could do that with just like a closest bullet, but these days a lot of designers are asking for penetration in the bullet code, so you can do the entire bullet raycast and say, collect everything along this bullet trace. Sort them by order of distance, and then you can kind of process through that list until maybe you only want to hit 3 metal things before you stop the bullet, or you want different penetration for different materials. We use it like you could use an all ray trace for that. As I was saying before, like can I move my helicopter forwards? Maybe create some kind of bounding shape for the helicopter, a sphere or a convex hull of some sort. And as you've got some game code that's trying to drive the helicopter around, the player's pushed forwards, you want to check, can we move forwards, or is there a cliff in the way? You could cast that shape forwards and see what it's collided with. And then, as I was saying before, like, hey, I want to teleport this player to this location. We've got some teleport mechanic, or maybe it's respawn for a multiplayer game. Like, if I put them at this location, are they going to be inside something? Is this a bad place to be? Like, has a car just moved into where I think the spawn point is? If it is, you'd want to do this kind of check. So that's kind of, we've now got a physics API that we can put rigid bodies in with whatever shapes, we can simulate, we can constrain, we can run queries against them. Everything's great if you're making a single player game. If you're making a multiplayer game, then we have a whole load of other fun excitement. I'm kind of going to restrict myself today to talking about client-server architecture, mainly because that's what I do, but it's, a lot of the similar things kind of will be relevant if you're doing lockstep peer-to-peer or even full mesh-based simulation. So this is kind of a standard dedicated server. It's got a server machine that sits somewhere, probably in some building that we own or pay people to have. And then you've got all of your clients sitting out there connecting to that server. They're not talking to each other, they're just talking to the server. If they want to send a message to another client, it goes via the server. It means that your server probably wants to have a fairly decent network connection, but your clients don't really need to be that super awesome. There's obviously the variant of that, which is kind of a client-hosted game, where one of the clients is also being the server. So this tends to happen towards the end of life of a game with dedicated servers, or if your game team can't afford dedicated servers, you can just have one of your clients, probably one who is well trusted, become the server temporarily. Does mean in a console game, you've now got on the same machine, you're having to run a server and client at the same time. You've got those memory and CPU costs, that you can't just have your client be the limit. You've now got to be able to run a full server at the same time. Obviously, for a big multiplayer game, you're going to want to trust the server as much as possible. They tend to be the authoritative decision maker on what happened in the game. In a dedicated server, we own that server, so we trust it wholeheartedly. We know that the code running on is ours, as long as it hasn't been hacked in some way, it is fully trustworthy. In a client-hosted game, that's when we tend to get hackers kind of jumping in, and you get people wanting to be a host. They tend to have big, beefy internet connections, and in generally be the kind of ideal host that you want, except they're a hacker, and then they've modified code locally on the machine, and they're being nasty. But these are kind of our two fundamental setups that we have. And then the way that we kind of simulate those servers and clients is the server's authoritative. It does its simulation, and then periodically, every 100 milliseconds, every 50 milliseconds, every 250 milliseconds, whatever your game's decided on, it'll send out a snapshot of the game state. It'll send that across the network. So it's like enough information for a client to entirely replicate what's going on in the world as far as the server's concerned. Clients then usually, they don't run now, they run in the past. So only 100 milliseconds, 200 milliseconds, whatever it is, ago, basically the distance between the snapshots. We run clients between the previous two snapshots. So at any point, just by interpolating between those values, we can kind of tell what the server knew and where a server knew an object was going to be. And it definitely was there. Like the server already told us that it happened, so we're not kind of guessing at anything. Problem occurs when we have packet loss and we don't get a snapshot in time. So now we were iterating between two snapshots. Time-wise, we reached the time of the second snapshot, and we were expecting to have a new next snapshot. We haven't got it. So we kind of predict. Usually it's poorly predicted because we really don't know what happened on the server. You can kind of guess, but if there's players moving around or AI moving around, you're not normally simulating that on the client, so you just keep people going in a straight line or stop them where they are. If you ever played a multiplayer game where you start seeing things pop around, probably what happened is that your network connection was getting terrible and you just missed a couple of snapshots. That's fundamentally the environment that we're kind of dealing with. So, with the latest kind of consoles and I guess latest PCs, one of the awesome things for anybody who's kind of worked in the industry for any amount of time is at this particular point in time, we are not memory bound. Like we've got almost more memory than we know what to do with. I'm sure if you ask me 6 months from now, we'll be scrounging for every kilobyte we can find. But at the minute, memory is awesome. CPUs have got faster. Again, like we're kind of dropping off the last gen and moving towards the next gen. We're getting a lot faster. We've got a lot more grunt available to us, and it's in some ways easier to use. Which means that the design teams are thinking up lots and lots of new features, but rather than just make individual things more complex, most of what they're doing is scaling up the old systems, where before they'd have 20 items, now we have 200 items. Problem is, the elephant in the room is that bandwidth really hasn't increased by any significant amount at all compared to what we're doing with memory and CPU. So we can put 10 times as many objects in the scene, but we can't communicate 10 times as much information about the scene. So when we're kind of integrating a physics system into a network game, it's really important to kind of make sure that your bandwidth is your additional bandwidth is as close to zero as possible. Take a few minutes to kind of talk about the techniques that we use to do that. First thing we do is the concept of a master-slave world system, where we first realize that the client is simply a copy of what's going on the server. Like it's not authoritative on anything in the game state. That's what the server's job is. So the client, all it needs to do is copy what's going on the server. So we'll let the server do the simulation. And then when we get the game state, we don't need to do any additional simulation. All we need to do is replicate the game state. Well, that's really easy to do on the client. We can just position, like make everything a keyframe body and just position it wherever the snapshots are telling us that we should go. In fact, it's entirely possible then that your client-side world may not need to simulate anything at all. You might just be using it to update some things and do some range shapecast inside and save a lot of CPU that way. It depends on how your local client predictive behaviors are for vehicle and player. The problem with doing this kind of thing where the client is not actually doing any simulation is, let's imagine this happened on the server between two snapshots. The snapshots are the position of some ball that's bouncing on the ground. It kind of starts up in the sky, bounces off the ground, and goes back up again. What we see on the client is this instead, because we just interpolated between the two positions. We entirely missed a collision. If we had client-side events for playing sounds, we're not going to notice one there. We're not going to play a bounce sound. So probably the server is going to have to additionally send some kind of event system for when objects collide, which is some additional networking cost. But in general, still, it's kind of a good general technique to have. So then, kind of given that basic setup, there's a number of simulation systems that have effectively no additional network load. The first is static bodies. They don't move, so we don't need to send any information about them. Like we know when they were created, we know when they were destroyed. Usually they tend to be the world anyway, which is kind of created at level load. Client knows that, server knows that. doesn't have any additional network load. We don't have to send in, we don't have to, every frame we don't have to send its position because we know it has never ever moved. Keyframe bodies are a little tiny bit more complex, but if we kind of go with the concept that their position and orientation and speed is entirely driven by other gameplay systems, those gameplay systems are probably synchronizing the data for the rendering engine anyway. So we can just rely on the client and server versions of those systems to kind of push directly to the physics system. We don't have to add any additional physics communication. You get this kind of behavior, where you've got the server game system is feeding the server physics world. It's doing its own network comms that it was doing anyway for the renderer. And then the client game system is pushing to the client physics world. So we haven't added any network bandwidth for our keyframed objects. This is a great example. I imagine the designer wants to have an animated welding robot. It's got like 5 rigid bodies, there's different parts of it, and the animation starts when the player hits a trigger box. Let's say they walk into a factory and we want to start the welding robot moving kind of as they walk in. Literally the only piece of data that we need to send is when that animation started. Because the animation is going to be deterministic, so the server and the client, as long as they both know when the animation started, we can tell you at any point in the future where that animation is, where the bones are in that animation, and where the rigid bodies should be. We don't need to communicate any information directly about the rigid bodies over the network. Well, I kind of cover static and keyframe bodies. The biggest problem is dynamic bodies, which are in a continuous simulation. They tend to be very difficult to accurately predict with any kind of confidence. If you've got a deterministic simulation, you can set up the server and client worlds exactly the same, as long as you start them up exactly the same way with everything in the same places in memory, and step them forward with exactly the same delta time. Then yeah, you're probably going to be accurate. Problem is, if you miss a snapshot and the client now starts mispredicting, when you finally do get that snapshot and realize that you made a mistake, the amount of data that you need to rewind a continuous physics simulation is not just the position and orientation and speeds of the bodies, but there'll be collision manifolds and caches and constraint data and huge amounts of data that might be 3 or 4 megabytes, which you can't send with every snapshot. So we can't kind of do client-side prediction of dynamic bodies with any real confidence. Instead, in every snapshot, we're going to have to include the position and orientation of every dynamic body in every single snapshot. So if you've only got a couple, that's not the end of the world. If you've got a lot, then this is where bandwidth in physics simulation really starts to stack up. Because effectively what you've added is this to the game. Like the server physics world is now having to send a whole lot more information to the client physics world. So like almost everything in video games, the solution to this is where we can, we fake it. You first of all have to realize that a lot of physics-based systems don't have any feedback into any other gameplay systems. So they don't need to exist on the server at all. If you've got a ragdoll or some debris or some particle effect physics, it's just there to look pretty to the player. Nothing, if you've got no gameplay system, if none of the gameplay systems care about where the ragdolls are, then the server doesn't care where they are. They might as well not exist on the server at all. We just simulate them flat out on the client. No network load because the server doesn't know about them. And this is probably the most common kind of optimization for network-based physics. If you look at this kind of exploding vehicle from, I think it's probably from a Call of Duty game of the past, you can see like a vehicle exploded. What happened on the server? Well, there's probably the hulk of the vehicle, which maybe changed shape and started playing an animation. Well, the network load for that is, okay, fine, we need to send the point at which it started playing the animation and destroying itself. Maybe that's even a single bit for that vehicle. Maybe all it does is explode, so it just needs to send 1 when it's exploded. On the client side, we also play that animation and swap the model, but we also fire off the particle effect, we kick out the drivers as ragdoll guys, we throw some bits of debris off, we add some destruction parts to the scene, we do all of that stuff, and literally the entire network cost was still that single bit of, hey, the vehicle got destroyed, or a single integer of hey, play the animation starting at this frame time. So I just want to conclude by basically saying like the purpose of physics simulation, as far as I'm concerned, in a game is twofold. It's fundamentally kind of providing information to high-level gameplay systems and events, so that systems like AI and gameplay can make queries or know where objects are. But it's also, you're trying to improve the visual fidelity through believable dynamic simulation, so that explosions look prettier and it looks like there's stuff scattered around the level that actually moves as you'd expect in the real world. We should, when we're doing network gaming, we should kind of rely on gameplay systems to communicate the game state as much as possible. They were probably doing it already, so the additional load is likely close to zero. And for dynamic bodies, we should try and keep them client authoritative whenever we can. If you have to have one on the server or a rolling barrel or something, great, but try and keep as many things on the client that we can. That's pretty much it. Any questions?
So what if you have something like you want to know that suppose I throw a grenade now, where is it going to land and is it going to collide with something? So something the AI, sorry, something the AI could use.
Yeah. So the problem with predicting physics in the future like that is normally a complex system is going to have a lot of linear damping on the object. You don't know whether there's a car going to move in between or anything like that. So the fundamental decision you normally make is, let's assume that nothing's going to move in our way. Let's not try and predict that stuff. We're just going to kind of do the arc. So then the question is, can you actually predict forward that arc? A lot of games, rather than actually throwing a physical grenade through the world, they kind of fake it. They have a simplified piece of game code that's literally just doing a straight parabola, in which case then you don't need to touch the physics world really very much at all. You can do a couple of raycasts and go, yep, looks like that one can go through. And the game to do that, because you don't want to add 20 or 30 little short raycasts to the game, instead maybe you only update once every other frame or something like that, just to keep the CPU load down. I wouldn't recommend that an AI does a lot of that, maybe the player, or if you've got a buddy AI, that would be fine. But your average AI, pretty much like you know that you're in cover, you can tag a piece of cover as, yeah, you can throw a grenade, and it's probably, you roughly know where the player is, so yeah, just throw the grenade. If it bounces against someone, goes back and kills them, you're not going to be super upset about that. The player's going to think that's awesome.
When you have objects which need both like keyframe animation and dynamics, so what happens? How do you deal with such things?
There's kind of two variants of that. You can have objects that are keyframed for a large portion of their life and then become dynamic. So that has a lot of kind of destruction elements. Like you might have some kind of building or robot or something that's keyframed for the most of its life, and then you cause enough damage to it and you want a chunk to kind of come off. It's fairly easy to kind of turn things from keyframe to dynamic. You can do that in a number of ways. Just have it disappear on the server and on the client kind of become dynamic. If you really wanted, you could have it stay dynamic on the server and then you'd have to network that stuff to the client. The other common thing is a lot of gameplay objects have more than one rigid body associated with them. You can have those, like some of the rigid bodies are keyframed and some of them are dynamic. So maybe you can have like a chandelier where the object, like the main portion of the chandelier is keyframed, it's swinging back and forth from some wind simulator that you've got. And then you've got some dangling pieces of crystal that are hanging off it that will be dynamic and maybe only exist on the client.
Other questions?
Oop, this got a bit slow.
When did you start doing game physics? Was that always your emphasis? When you
So
started working on
I started working at Sony 12 and a half years ago. I did some back-end R&D stuff, PlayStation 2 era, and some UI, and then kind of after a couple of years I kind of started into physics. I've kind of been doing it ever since, so like the last decade or so. It's what I love doing.
Okay, and did you learn all the physics stuff on the job, or did you go take
Yeah,
classes?
I knew nothing at college. Like my degree, I have a master's degree in comp sci, no game tech at the time at all. So like I had some graphics classes, but that was it. Everything was learned on the job or from reading books or whatever.
Okay.
I think these days you're kind of lucky that you can go and grab an open source physics engine like Bullet and plug it into whatever simulation you want to and kind of roll with it. Okay. Any question?
Some exceptional material like mud or glass will require another mechanism to crash or collision. Right.
Yeah.
In that case, do you have any manual like those kinds of objects, or just use the fundamental algorithm that the GPU or base game engine provides?
For like breaking glass, you mean? Or?
Yes, some essential object like glass or mud or something.
So destruction is kind of a whole separate topic. It's normally like when you get a collision impact against something made of glass, you probably would have had either some runtime fracture algorithm, which tends to be very expensive, or a pre-generated kind of fracture behavior, and then once the collision against the glass reaches some threshold, you just decide to break it, and then you can just break it from a pane of glass into lots of small pieces.
So it is good strategy to make a pre-animation data of each object or some kinds of other data method?
Yes, definitely. Trying to calculate a fracture algorithm in real time, you can make things that look absolutely awesome, but they tend to take like 5 to 10 milliseconds to generate, which you just can't afford, particularly if people going for an eFrame class. So yeah, pre-generate it. Either with pre-generated algorithms, pre-generated geometry shapes or whatever, and then you just have something that just kind of turns it from plain glass into shattered pieces and pushes them out.
How detailed is your integration? What order of integration? Do you first order integration, second order integration?
I call the middleware that we use and let it do its thing. And these days, most of that stuff is mathematically, it's way beyond me. It's like people with multiple PhDs have been working on it for 15 years, and you go and talk to them, and there's some crazy stuff going on now. I just kind of let them do their thing. I think kind of the one thing I've noticed in kind of coding over the last decade is it's getting more and more specific what your job is. And I'm not only a gameplay engineer, not only a physics engineer, but I'm like a physics middleware implementation engineer. There are people who do like physics kind of back-end stuff, and most of those guys these days tend to work for middleware companies, though there are some still in video games still. Anyone else?
Any open positions in the physics realm at Infinity War?
No, it's mine.
That's it.
To tell you the truth, yeah, I mean, we're always hiring.
They're always hiring.
Always hiring. Like if you're good at it, like I can always find a job for somebody to do.
Okay. All right. All right. Thank you very much.
Thank you. I do have some exciting